In this tutorial, I'm just going to explain how you calculate your mass transfer coefficient. I hope you all remember what is KLA value using a dynamic method. I already explained in the lecture time how do you measure your oxygen transfer rate using dynamic method. I explained few of the techniques. I also explained how to get this value using a static method. Yeah, so if you don't know the theory, just follow the other lectures which I already uploaded. So here I'm just going to show how we perform the experiments in the lab, like or somebody or like sorry, I think I covered already in the tutorial, so in the lecture, sorry. So in this tutorial what I'm going to say is like you already done the experiment, you have the experimental data, and you want to get your mass transfer coefficient from the experimental data that you have. Yeah, so I will just read the problem that will help you to understand what we are going to do now. Yeah, so the air supply to the fermenter was turned off for a short period of time and then restarted, and then a value of C star means that's the solubility concentration of oxygen of 7.3 milligrams per liter has been determined for the operating conditions. So we maintain some condition, say like temperature, some agitation speed, and at that particular condition your solubility or the maximum that you can dissolve your oxygen is 7.3 milligrams in 1 liter of your fermentation broth. And this fermentation broth contains live cells, which mean once you switch off they will consume your oxygen, and once you supply your oxygen they are going to breathe at the same time you are going to transfer the oxygen. So it will happen simultaneously. So once you switch on the air, you are going to transfer the air. At the same time your microorganism will never stop breathing, which means something is transferred and something is utilized simultaneously at the same time. So that's why we call this as a dynamic method. And then so these are the experimental values. So somebody already performed the experiment and then they got some values. So I'm just going to remind you what this experiment is about. So you have a fermentation unit. Just assume you have a perfect mixing condition, temperature, pH, all are good. Yeah, so you are supplying oxygen. So just assume oxygen is at your solubility limit, 7.3 milligrams per liter. So once you cut your oxygen, it's going to drop like that near zero, and then you supply oxygen again, oxygen on, it will go back, and then it come back to your saturation concentration. You cannot dissolve more than this number because that's the solubility limit of your fermentation broth for oxygen at the studied experimental conditions. It can be room temperature or it can be slightly above or below the room temperature. So for the moment, just assume somebody did the experiment, this particular experiment, and then they have the value here, this part and this part. So they got this value already. Yeah? So I'm just going to show the experimental data. So you have time in minutes, you have concentration milligrams per liter. So how we measure this concentration? We put some probe here, some conductivity meter, so that can be correlated with your O2 oxygen concentration. So we can monitor your oxygen concentration, everything online. Yeah, so that's the whole idea. That's how we do the experiment in the lab. So you have -1, so and then time 0, so that's the time at which you switch off your air. So that's at 4.5 milligrams per liter, and then it's going to drop down, and that when you 7th minute the oxygen concentration dropped to 0 here, and then you turn your air on at this point, and then which means your oxygen concentration is going to increase from 0 back to your solubility limit. So this is your solubility limit. If you plot your O2 concentration and your time on the x-axis, you will get some plot like that, yeah, for this type of experiment. And then eventually your concentration is increasing, 4.3, if you 4.4, and if you wait some more time it will eventually reach to your solubility of 7.3 milligrams per liter. So 14, 15, 16, 17th minute it reaches 4.4 grams per liter, so sorry, milligrams per liter. So milligrams of oxygen dissolved in 1 liter of your fermentation broth. So now you need to calculate KLA for this problem. Yeah. So how to do that? So we already know the change in concentration with respect to time is oxygen transfer rate minus oxygen utilization rate. So this is, I already derived this one. This is from your Whitman theory minus QO2. This is Q suffix O2 multiplied by X. So this is for oxygen transfer rate. This is your oxygen utilization rate. They both have different units. I already solved it. So for this part of your experiment, just the, sorry, I forgot to mention, I already plotted it roughly. I don't have a graph sheet, so I just plotted. So if you plot all of your data, so this is the point of air off at 0 minutes, and then you see the concentration decrease until 0, and then this is air on, point air on, then it starts to increase again, eventually reaching going towards your solubility limit. Yeah? If you allow, it will go to 7.3 after some time. So at this part, so there is no oxygen transfer rate, so only oxygen utilization rate, because you already cut your oxygen supply, which means you are not transferring anything, but your microorganisms are consuming your oxygen. So this slope corresponds to oxygen utilization rate, and this one is corresponding to oxygen transfer rate. Yeah? Oxygen transfer plus some of them, some of your microorganism will continue to utilize your dissolved oxygen in the liquid. So that's the whole concept. So now you have this formula. So we are going to use this formula to calculate KLA. So how to do that? Well, so first let's calculate the oxygen transfer rate. So oxygen transfer rate, this is really easy to sorry, oxygen utilization rate. Oxygen utilization rate, that's easy to calculate. So you have from air off to 0. So you take only this part of your data. So we know that so for the first part of your experiment, when you switch off your oxygen supply, your dC by dt will be equal to oxygen transfer rate minus oxygen utilization rate. This part will become 0. So dC by dt will be equal to 0 minus OUR, that will be equal to minus QO2x, or minus Q suffix O2 multiplied by X. So that's your oxygen utilization rate. Yeah? So you can integrate this equation. So dC by dt is equal to minus QO2, this is a constant, X multiplied integration of dt. So this is a constant value. So you can integrate with respect to your experimental condition. When T is equal to 0, your concentration will be equal to C0. This is your initial concentration. When T is equal to T, your concentration will be equal to C. So you derive them. So this is nothing but C minus C0 is equal to minus QO2 X multiplied by T. So let's call this as equation 1. So what it states is like this is almost like a y is equal to mx plus c. C is equal to c naught minus QO2 multiplied by x into t. So you can plot c versus t. You have a negative value, so you will have a negative slope. Your intercept will cut exactly at your initial concentration of your oxygen. That slope will be equal to minus QO2 multiplied by x. So this is nothing but your oxygen utilization rate. So all you need is to go to this plot, take this part of your data. It's very simple problem. Yeah? If you know it, you can do it in less than 2 minutes or even 1 minute. So you plot time versus O2 concentration. If you want, you can call a C, milligrams per liter, concentration of oxygen expressed in milligrams per liter. It will start from 4.5, that's your initial C0 value. You will get something like that. Somewhere it cuts at 0 here, around 7 minutes, I think. and then the slope value, this will be equal to minus 0.645. Yeah, so this is equal to minus qO2 multiplied by x. Therefore qO2 multiplied by x, that will be equal to 0.645 milligrams per liter per minute. So that's how you calculate your oxygen utilization rate. So now you need to calculate your oxygen transfer rate. This is even more simple. Yeah, so for that you have to, you know how to expand that equation. So dc by dt is equal to oxygen transfer rate minus oxygen utilization rate. This is equal to KLA C star minus C minus qO2 x. This is such a simple problem. All you need is to expand. It's not difficult at all. KLA C minus qO2 x. This is dc by dt. So let's keep it like that. So if we look at this one thing is clear. Yeah. KLA is a constant, C star is a constant, oxygen utilization rate is a constant if you have your microbial concentration equal to x. So only thing is like C is a variable and KLA, that's the one you have to calculate. So you can take all the constants on one together. You can put all the constants together. dc by dt equal to KLA C star minus qO2 multiplied by x minus KLA into C. So this both of these quantities are constant. So let's call them as alpha, which is a constant. So dc by dt is equal to alpha minus KLA into C. So this is such a simple problem. Yeah. So all you need to do is plot dc by dt versus C. You will get something like that because you have a negative slope here minus slope, that will be equal to minus KLA. So therefore KLA will be equal to slope. So if you multiply minus 1 on both sides, so this will be your answer. So all you need is to, if you go back to this graph, you have this concentration versus time. All you need to do is take dc by dt of this particular part where something is getting transferred. So let me change the color or highlighter. So all you need is to just look at this particular point. Okay, why it's so all you need is to focus this area. This area. So we know concentration versus time. So we take dc by we take this part and then dc by dt and then plot it against concentration, and that's it. From that slope you can get your KLA value. So how to do that? Yeah, all you need is to find a function. So just to take this part alone. So let me go back to the new page. So go to new page. So time versus concentration milligrams per liter. You have something going on from here to here. So you fit a line through this point, and then imagine, say this line, for your problem, this line is like a a polynomial equation. So C will be equal to minus 0.0482 x square plus 1.5827x plus minus 8.5375. So that's your equation that can describe this particular part of your kinetics. So this one. So C is equal to minus 0.482 x square sorry, or by, instead of x you can replace with t plus 1.5827 t minus 8.5375. So this is your concentration as a function of time. So how to take, just differentiate this with respect to time. That will be equal to minus 0.482 multiplied by 2 into t to the power of 1 plus 1.5827. So that's it. So all you need is like just plot time. You can, if you want, you can start assume this one is time t is equal to 0, and then you can get the remaining numbers. So just take time, say like 0 1 2 3 4 and so on, and then here dc by dt, and then just plot it, just add this number here. Yeah, so just substitute t is equal to 0, this will be 0 in this equation. Yeah, and then put t is equal to 1 in equation 2, and whatever the value you get, you just write it here, and then put t is equal to 2, and then whatever the dc by dt value, you write it here. Yeah? So that's how you get your dc by dt from this problem. Yeah, so it's not a difficult one, you can do it easily. And then you also know what's your concentration at that time. You can also one more column, concentration from the, if you go back to a problem, we have starting from 0 1.2 to 2.5 2.8, and time you start from here 7 8 9 until it goes to 17 minutes 2.8, and then it goes up to 4.4 milligrams per liter. Yeah? So this is a really easy problem. You can try to solve it by yourself. I already show how to do it. I will give the answer as well. So all you need is to plot dc by dt, and concentration in the x-axis is milligrams per liter, milligrams per liter per minute. So you will get some value like that. You take a slope, best fit line, so that line will be approximately equal to minus 0.2755 c plus 1.1362. Yeah, so your c will be equal to minus 2755, sorry, dc by dt will be equal to c plus 1.1362. So what is this? So this is nothing but your KLA, just a unit of 1 by minute. Yeah, this is such a simple problem. Yeah, like all you need to know is how to fit your data. So I'm going to stop the recording now. Thanks for listening.